Welcome to today's webinar. So it's a second part of the HYDAC e-mobility webinar story. And we would like to introduce you to today's topic of unlocking maximum power, how to benefit from a modular model design for electrified mobile machinery. Today, it's Bernhard and me who have the honor to present our content. And first of all, we would like to start with a short personal introduction. So Bernhard, please introduce yourself.
Thank you, Fabian. Yeah, so my name is Bernhard. I'm Managing Director of Engiro, and I joined Engiro roughly 6.5 years ago. I studied electrical engineering before that at University of Aachen, RWTH, and did a PhD for roughly 6 years on high-speed electric drives and range extenders. That's the way I got introduced to Engiro, started working there, as I said, 6 years ago, and gradually took over the R&D team and now manage the engineering part of today's webinar.
Right, thank you. So my name is Fabian Schneider. I'm head of sales for Engiro since beginning of this year. I've been studying also with an engineering background, studying sales engineering and product management, and been working in the e-mobility technology segment for roughly about 10 years, and always in different kind of sales position, and being now in charge for our sales effort, sales teams within our Engiro company. Okay, good, perfect. Then I would say let's start with some more content. First of all, we would like to start with, let me say, small introductory part to get a little better comprehensive understanding on market situation and how we see the current demand and also the further development over the next years. And also then to describe the challenges which come specifically with the applications which we define herein. So long story, keep short, current challenges, and you benefit from this webinar to give you a comprehensive overview first. Looking first of all at the so-called hype cycle of electromobility, I think everybody of you is nowadays seeing the newspapers, so especially in the automotive segment, there's some kind of reduction of expectations inside of e-mobility technology. Nonetheless, so specifically for the branches we are focusing on from HYDAC and Engiro side, so that means effectively most of the applications we are nowadays applying to is off-highway industry, so construction equipment, agriculture, municipal vehicles, but then also part of different branches, marine applications. We see that we are still in, let me say, kind of valley of tears. That's pretty obvious. So this year is not the best year for this kind of developments. But we're also moving right now from the valley of tears to kind of stable plateau of productivity. So we have been starting roughly 4 years ago with a high expectation in the off-highway electrification. This does not necessarily mean only battery electrics, but can also mean hybrid technology. Right now, expectation is going down a little bit, and with the projects which we are working on together with you, we see that we're getting to a stable situation over the next years, which gives then also high maturity on the market level for battery electric or hybrid machines at all. And this is something which is also publicly committed. So we have here an extract of market analysis, so which is analyzed in different kind of statements from large OEMs focused on the manufacturing of construction equipment. So what you see here is very popular names on this one. I think this pointer does not like me too much. So we see obviously that there's all the commitments for internal combustion engine, obviously, but all of the companies which are nowadays have a strong market share with construction equipment already offer battery electric vehicle solutions, at least in the smaller power range. and also looking at electrification of the larger machines, not necessarily then battery electric, but also with regards to further development of diesel hybrid technology solution. And we see also further innovation trends for other technologies like hydrogen too. But for us, obviously, the major topic lays on electrification of machines. And even though if we're looking still back on the hype cycle of e-mobility, so at the moment market situation is not the, let me say, optimal one, we nonetheless see that the world is moving significantly. So we see, for example, large commitments by the mining industry that the largest mining companies worldwide stated to cut 30% of their carbon emissions to 2030. Effectively, this means that most of the mining fleet needs to be zero emission in 2030 to achieve these kind of targets. We see zero emission zones growing in different regions and countries worldwide, affecting also the fact that construction equipment needs to be zero emission too. We see that also different countries like, for example, Norway or Netherlands or Canada also providing incentives for electrification of fleet solutions. We see obviously the trend that emission regulations are tightening more often, and by this bring also a lot of problems, let me say, with regards to further reduction of particle emissions with internal combustion engine technology only. So effectively meaning also their electrification helps to achieve better emission standards for the future, and which is key of the future discussion also to ensure that electrification will be successful in the market. Total cost of ownership is one of the major arguments. And from this point of view, we just would like to share one of the insights where there is some analysis already been made where we see total cost of ownership for an internal combustion engine versus total cost of ownership for battery electrics, where in the end the total cost of ownership for battery electrics is lower in a lot of application cases nowadays compared to internal combustion engine applications. And one of the main aspects which should not be underestimated in this case is also the downtime costs for an internal combustion engine application versus a battery electric one. So far, so good. Coming more related to, generally speaking, to the challenges which we see with the with electrification of the off-highway industry. One of the big constraints we see in the market, which we feel in our daily business, is that from pricing level, the expectation is there that the solutions which we offer are in the same range as what is nowadays supplied to the automotive industry, which brings us some conflicts due to the fact that comparing numbers from automotive industry, just really regular numbers. So looking at last year's production of light vehicles, passenger light vehicles. So last year there have been roughly been sold 70 million light vehicles being sold, compared to 1.1 million construction machines manufactured then in 2023. So obviously the volumes are significantly different, but the price pressure, the cost reduction pressure is in the end the same. The expectation level by the end customers is very similar. And this brings us in conflict because we need to provide solutions, produce them at lower quality, but also need to ensure high competitiveness to help for your success. And the other aspect which is driving cost inside of an mobile machinery, is the complexity of this complete system. So today you will see in our webinar we talk a lot about hybrid architecture, because from our standpoint this is one of the most complex architectures you will find on machines. And specifically you have the challenge that you have different kind of applications which needs to be provided with power in the machinery. So for example, we have hydraulics, what we see here. Maybe like that. Perfect. So we have hydraulic systems, which needs to be actuated by electric drive sets. We have then the traction drive systems, which is then electrified. We have generator solutions, which are finally then providing from the diesel engine the energy from electrical from mechanical energy to electrical energy to feed all the different consumers inside of a machine. And you have further complexity with regards that you need then obviously a cooling system, you have a battery system which is communicating, you have then other components like VCU, etc. But so the main aspect here is you see the number of actuators is growing, electric actuators is growing in a mobile machine. And at the same time, also the requirements are different. So an hydraulic system needs to provide different performance characteristics than a traction system. And the generator system at the same time needs to provide also different performance characteristics than compared to the hydraulic systems. How to bring all these aspects together, how to make sure that then still the competitiveness is given, how to make sure that finally all these different requirements can be fulfilled. This is something we would like to show today. And then I hand over the summary to Bernhard.
Yeah, thank you, Fabian. So as we saw, we have a increasing machine complexity. We have very strong challenges, mainly due to volumes at the moment. So we have volumes per whole market, per vehicle, which are very kind of low compared to the automotive industry. And each of you, our customers, has different machines. So this complexity and the variability is very high within the company. And at the end, what needs to be provided to the end customers of our customers is a smart machine and an added value. We cannot just replace a combustion engine machine with an electric machine. Ideally, we need to reduce cost or add value. And for this, a strong partner with a highly variable portfolio is required. We already showed in the webinar earlier this year on electrification kits how we believe that solutions are actually working on this. And we now today would like to focus more on the electric drive system, as we from Engiro side are mainly focusing on the motor. This will be the focus in the next slides. So what is the added value from Engiro to you, our customers? I would quickly start with an introduction on motor technology available in the market, because in addition to the machine complexity, there's also a technology complexity. So different machine types, electric machine types are existing. In the past, especially material handling, the induction machines were used. But then in the automotive industry and also in the construction machinery, the focus was mainly on permanent magnet synchronous machines. The reason there is that they offer high power density, high efficiency, and high torque density, and therefore for the applications, as we will show in the later slides, are very well suited. There is additional machine types, such as, for example, synchronous reluctance motors or externally excited motors, which are offering alternative advantages. The point is that these technologies have all different pros and cons, and typically you could analyze them in a kind of matrix way. And this is a little bit subjective, because depending on the advantages you are looking for and depending on the feeling you have, you can tweak this kind of comparisons. But some general things apply. For example, due to the added magnets, the torque density and the power density of the permanent magnet synchronous machine is typically very high, because field doesn't need to be applied from external. We do have a little lower efficiency at high speed compared to an induction machine, for example, but this is really depending on the application if this is important. And typically electric machines offer very low torque ripple and NVH excitation compared to combustion engines. So typically the noise level in the machine is lower than before. This applies for most machines. There is exceptions, but typically this is the case. Why do we focus on permanent magnet machines, or the design we have? Some characteristics and benefits we can deduce from this. As I said, the permanent magnets apply a field to the machine which doesn't need to be applied from external. This leads to a reduced dimension and weight, so very compact and high torque machines. We have a high efficiency, because the field doesn't need to be applied. This means it doesn't create losses in there, and a dynamic control is possible. And this adds in the fact that it's reducing weight in the machine, also that it reduces energy consumption. We at Engiro use embedded permanent magnets, as you can see here on the left. This is the case because like this, the magnets are integrated in the rotor. They're not at the surface, so they are withheld by the steel above it. That's suitable for high-speed applications. It's good for durability and safety, but it's also offering the fact to exploit reluctance torque, which is good for shaping the performance plots, which you will see later on a lot in our slides. So for example, for traction or for wide range applications, this is very helpful. What we also focus on is distributed windings with round wire. We get a lot of questions nowadays why we are doing this. First of all, in the distributed windings, this is the case because distributed windings compared to concentrated windings offer lower harmonics in the machine, so lower losses and higher power density. We have lower reduced AC losses because we can use with round wire smaller wires compared to hairpin, for example. And the main point for us is also the flexibility. As you will see later in our slides, we can tailor our machines to your needs in terms of voltage and power and operating range, and that is much more flexible possible with round wire rather than with hairpin, where the flexibility lies only in the range of 4 to 12 turns, where we are working in the range of 6 to 200 nearly in our machines. How do we create then a modular portfolio? And I guess most of you which are not attending the first presentation from our company know this, but our portfolio will show also in one of the next slides in total is mainly built of several motor types, and within each motor type we are offering a length variability. So increasing the active length of the electric motor, the torque in the low speed range, in the space speed range we call it, is actually going up at a constant current. So at constant current supplied from the inverter, we get at a longer machine a higher torque. We have a little reduction in power in the field weakening range because the inductance also goes up and therefore the back EMF goes up and therefore a little lower power in that range. This applies as well for S2 15 or 30 minutes, so shorter term power as well as really short term overload power for 30 and 60 seconds. So it's quite linear that the power increase actually increases this possible torque as long as you disregard the thermal behavior of the machine. In efficiency, what's important that longer machine, the high efficiency area is staying at a similar speed range because that is mainly influenced by the design of the rotor, and this doesn't change within one design to be able to produce that variability in length. The second factor we are varying is the winding number, and the winding number is, if you keep this length of the machine constant, has the effect that at a specific torque level you get a lower current. So you see here the solid line is a higher winding number, while is a lower winding number, while the dashed line is a higher winding number. So with a lower winding number, the current goes up. It's much bigger than in the higher winding number, but the nominal point goes up in speed as well. So at that point here, the dashed line, as I said, has a higher winding number. We already have the constant power range at a lower speed, while at the lower winding number, we can supply that base speed range with that base speed torque for a longer time. So this gives you the offer, turning this around in voltage to adjust the operating range at the battery voltage of the machine. The effect is similar also again in terms of the overload powers. The efficiency again does has a certain effect. We will see this later in some slides in a better way based on measurements from our test bench. But again, the speed range where optimal efficiency lies stays very similar due to the rotor design. And so what we can build from this, and there I would like to hand over to Fabian again to drive you through our portfolio, is this shown on this slide.
Thank you, Bernhard. Yeah, so as Bernhard mentioned, so we have a wide variety within our product portfolio. So at the moment, we're talking about in total 4 different product families, one new to be announced very shortly. So you're one of the first who is already then getting some knowledge about the new Model 2. The main difference aspect between these 4 or 5 motor families is nowadays that we separate or we differentiate the active stator diameter of these motors. And this allows us then to finally have different kind of torque characteristics, and by that also different kind of power characteristics achieved with this motors, and which is also counting heavily for selecting the right diameter and length combination is also the packaging aspect. So when we're looking specifically at this portfolio, starting with the low power motor, even low power does not mean necessarily low power, so looking at this power range of up to 30 kilowatt, this ones is the motors at the moment with from our portfolio with the lowest power range, which we have as air-cooled and water-cooled versions. And then at some point, when the torque of these ones is not sufficient anymore, and by that also the power rating is not sufficient anymore, then we move over to the next series, so to the 205 series. The aspect is, so we could achieve also the same torque with a 159 series, but then with a longer version, which is for a lot of different applications not suitable anymore, because at some point then you're getting in conflicts with different packaging requirements. And this is one of the main reasons why we finally have different kind of diameters inside of our portfolio. So 259, 205 and 260 as the fast speed motors, and by this then we're wiring the torque capability. So just as a reference, then for the 205 series, for example, the maximum torque capability is something roughly about 400 Newton meters. 260 goes up to, at the moment implemented, realized up to 1,600 Newton meters, with the capability even to have a larger peak torque capability here too. And last but not least, then we also have a 370 series. So this is a little bit different from the generic approach which we were following over the last year. So the 370W series is then a low speed, high torque motor. So we have applications, for example, heavy duty traction applications, or marine propulsion systems, or even heavy duty pump applications where we need solutions which are operating at really low speeds with very high torque output. So effectively, speed means here restrictions up to 4,000 RPM, while the smaller motors like the 159 and the 205 are speeding up to 8,000 RPM, and the 260W is speeding up to 6,000 RPM. And in between those, we have seen a gap that we need an additional motor family which is providing higher torque compared to the 159 series at a smaller package. So effectively, the length is an issue. We have customers which cannot implement the 159 series length inside in their applications, and for this reason we right now also start to introduce a new product family. Diameters larger than for the 159 series, so we're providing higher torque output by it, and we can reduce the length so that finally it's a kind of optimized product, for example, for near wheel installations, assembly groups. This portfolio helps to finally adapt to very different kind of applications for hydraulics or traction drive systems and so on, and this is what we will explain over the next slides, then in different kind of case studies. Before we come to that, we just want to make sure that it's understood that we are not talking about fictional products. Yeah, so we see with regarding to market activities, there's a lot of promises inside of the markets for electric motors which are available or which are announced to be available. We clearly want to state that we have manufactured more than 7,000 motors, not for automotive, but for off-highway industry, which is a significant number for off-highway electrification, and where we supply to currently roughly about 200 customers in more than 25 countries worldwide. With a variety in our product portfolio of more than 100 different motor variants, which we have nowadays available, and which is growing annually by the custom demand of you, because we want to have the ideal product in your application, which fits your needs for the right torque, for the right efficiency, and also for the right packaging. And so you see, we have a bunch of different applications. These all are real applications where motors are already in operations. How do we help you? That's the major question, I think, for this webinar. Otherwise, it would be wasted time for you. And so I think we need to deep dive right now more in the different kind of application scenarios. As we introduced, so we selected the hybrid powertrain architecture, as we believe that it's one of the most complex architecture from, let me say, different kind of functions which you need to establish in one vehicle. Just keeping in mind, so we talk today about hydraulic functions, we talk about traction functions, there we go again, and we talk also about generators. And for the traction, we even prepared some additional surprise. So we will talk about a direct drive solution versus also a traction system with transmission solutions. Before we then start with this topic, just some really major basics, because typically we receive a lot of requests. We receive a lot of questions then, what is the optimal product for our need? Obviously, so first of all, we're also looking at a system approach. We check, okay, what is most valuable for your application, and there we also look at the comprehensive system understanding. But today we're mainly discussing about the drivetrain, the electric powertrain system, and therefore we are mainly focusing, let me say, on the motor part and also on the inverter part. And looking at this, so the main things which is relevant for us to select the right component solution for you is the peak performance. So you see here numbers 1 and 3 on this exemplary plot. So it's about what is the maximum torque which is needed for this application, associated power, what is the speed range required for the peak performance, what is the duration of this peak operations, because there's a significant difference in if you're operating a motor on 10 seconds in a peak operation duty cycle, or if you want to operate the motor in 10 minutes in the same duty cycle. Continuous power, this is the major key at the moment for off-highway applications, what we typically see. So off-highway is most driven by continuous power demand, because the machines are typically all operated in a very constant duty cycles and very constant high productivity levels, where you're mainly looking at the continuous demands, and the continuous performance needs to be provided over hours. So just looking at multiple shift operations where machines are operating then 24 hours a day and maybe just being interrupted by recharging cycles, or even for hybrid applications where there is no interruption of the complete operation at all. Speed is super relevant information for us. So what is the maximum speed required for the nominal range as well as for the peak range? Voltage has a big influence finally on the power capability, but also on the nominal set point. This is something which Bernhard will explain more in detail then over the next slides. Cooling makes a major difference. So we see that performance is different at a coolant temperature, for example, 45 degrees to 60 degrees makes a difference. 60 degrees to 70 degrees coolant inlet temperature makes a difference. So as more precise you know the cooling requirements, as more precise you can limit those, as also in this case, as better cooling system you have, as more efficient system you have, and get the coolant temperatures down, as better we have the possibility to avoid any overdimensioning of components. And last but not least, also the topic of mechanical interfaces is a major part. So how do we finally bring then transmission together with the electric motor, pumps together with the electric motor, or any other kind of different applications? Okay, starting with the first item, generator case study, concentrating on the electric generator here in this picture on the bottom. So we're talking here about a diesel electric generator. So effectively meaning, looking at this combination, we have a diesel engine, we have an mechanically connected generator, electric generator. This is then electrically linked with the inverter. Inverter is then finally supplying DC supply to the DC grid, and by this then the other consumers inside of the DC grids are fed with power. We take a generic sample for this. So for this sample, we're looking at a voltage level of 700 volt battery, coolant inlet temperature of 60 degrees Celsius. And then you see the nominal diesel engine characteristics. So you see here that on this chart that we are looking at, at a maximum torque range of something about 462 Newton meters at a speed set point of 2,800 RPM. And at the same time, this is the most powerful nominal diesel engine set point, and also one of the most efficient set points. And for this application, the application foresees that typically the generator is most of the time driven in this kind of specific operation set point. So finally, for us, it's relevant that we need to consider that this operation set point is driven continuously for a long period of time without allowance on any kind of derating, because the diesel generator, diesel hybrid, the diesel electric generator needs to provide continuously same power level to ensure high productivity on the complete mobile machinery. We have a process inside of us, which I explain in this case study once, just to give you also some further ideas which kind of variety and possibilities we have for the selection of different components. So what we have is, let me say, first of all, a generic template, an Excel template, what we use first of all to pre-select, to limit a little bit the selection of different kind of motors. Because you can imagine with more than 100 motors in your portfolio, at some point you're losing the overview, which might be the optimal choice, and then some digital support measures like Excel templates and other tools, which we show then in the next slide, are really beneficial for selecting the right solution. So what we do here is, first of all, a static analysis of the requirements. So just keep in mind what I mentioned the slide before. So there it is. We have said 460 Newton meters, 462 Newton meters at a speed set point of 2,800 RPM, and we also calculated already what is the required power, so 135 kilowatt. First of all, we're investigating what this effectively means for the different kind of motors we have in our family. So just as mentioned, we have 4 different kind of product families at the moment. 5th is up to come. And as we also mentioned, you can also achieve the torque by increasing the length of a motor, which does not make necessarily always sense when looking at the packaging requirements. So typically we have the 159 series. We see here that the required minimal length of the motor would be 665 millimeters. So just the 159 motor is a motor with a typical outer diameter of 180 millimeters, and with a length of 665 millimeters, definitely not an ideal, let me say, packaging factor, and not manageable within our production facility too. So 159 we kick out for this kind of application. This does not match. 205 series, so 455 millimeters. Outer diameter of this motor is 220 millimeters, so it's, let me say, double the length of the diameter. Is an option, but not necessarily the ideal packaging factor too. So last but not least, looking at the 260W, so 175 millimeters minimum length, this sounds arguable. So finally, looking then at the next motor selection point. So we're looking at a 260W motor with an active stator length, in this case, longer than 175 millimeters. When you look at the motor code from us, which is from engineering standpoint really simple, so what we describe first of all is 260W, so 260 standing for the active stator diameter, and then the 200 stands for the active stator length. So effectively, this is over exceeding the required 175 millimeters. So first selection for the motor length is then 200 millimeters. Second part is about the winding configuration. So we have here then for the 260 a requirement that maximum winding configuration with regards to the voltage level, so 700 volt, is in that case 21. The winding configuration mainly depends on the voltage range, on the voltage selection. And this is something which is also then adjustable for us in different kind of motor types too. Bernhard will explain more in detail at the latest point also, which kind of effects might come out of that. So effectively, we see right now, okay, so we have a requirement of maximum winding configuration of 21. So one of our pre-selections of a potential motor is 260W 2020. In combination with an inverter, this inverter is providing, for example, a continuous current rating of 200 amps, 300 amps peak. But then at the specific analysis review of this, of the characteristics of this motor, we see that we achieve this torque 485. We over exceed the required torque 485 Newton meter, but this is just provided up to a speed range of 200 to 2,440 RPM. So this does not fit in the specific requirements which has been provided by the customer. Effectively, so we're then going for the next winding configuration, which we have then in our portfolio. So this is the 14. Is the 14 providing a better performance? Looking at the speed range, yes, 2,800 RPM. This is the, let me say, the curve where finally then field weakening is starting, but still the torque is not sufficient at this point. So 382 Newton meters. Why is that? Because we have different kind of inverter selections too. And what you see here is on this part is the different kind of controller models. So we see here an 800 volt inverter. So we have it with a nominal current rating of 200 amps. We also have it with a nominal current rating of 400 amps. And the current is finally limiting the torque. So effectively for this motor, so the 260W 2014 with the small inverter with a nominal current rating restriction of 200 amps is not sufficient for this application. But going for the next larger size of the inverter, 400 amps nominal, 600 amps peak, there we get to the target. So finally seeing, okay, 473 Newton meter is what this motor can provide, and speed range 2,800 RPM looks really good. So perfect. We have a pre-selected motor so far. Before we go then for technical proposal, we do another step in between. We have internal simulation models. And the simulation models is something which is based on validation programs in our house. So nowadays we have measured, tested a lot of different motor inverter combinations to give really precise information to you about the performance of our products. And these measurements are then part of the simulation model. So effectively, we're doing all the measurements on the test bench. So also outtakes of the test bench and on the next slides. We're showing a lot of things in the next slides, I think. And then we can finally figure out the realistic characteristic. And why is that important? So at the slide before, we have seen the static analysis. And right now we also need to look a little bit more on the more detailed on the dynamic analysis. So based on real measurement data. Because typically what you see on this kind of performance plots is when you're looking at on web pages, on different web pages of motor manufacturers, is you always have this great stable line on the same torque, and then at some point it's starting to drop. The reality looks a little bit different. The reality looks that you have some kind of waves in between because it really heavily depends also on the thermal behavior inside of the motor. And also you try to push the performance, the peaked performance as well as the nominal performance. And by this, then we have the possibility in our simulation tools to select motor, to select the inverters, consider the complete measured models behind at different coolant and voltage levels. So we do then validations at different voltage levels, we do validations at different coolant levels, and this allows us to give very precise answers and also technical proposals to you to say, okay, this product really fits your needs. So effectively what would happen is if you adjust here the coolant temperature, for example, to a higher temperature level, the nominal performance would drop, and the other way around. So if you're reducing, for example, the coolant temperature level, then the nominal performance would also increase a little bit. And these effects is something which we then also consider in our analysis. And then looking finally at this, let me say, target set point, so 462 Newton meters at 2,800 RPM. So we see here, we need to check on the blue line if we're still in the nominal torque capability. Yes, so the green dot is within the nominal torque capability. So finally, we can confirm this motor, also considering the inverter, is matching the requirements. And by this, then I hand over for the next slides to Bernhard.
Thank you, Fabian. Something I want to add on this slide is that the tool we're seeing here, we also built for another reason, because on the slide before you saw that Fabian was looking at static operating points for continuous and peak performance, torque and power, but typically you don't have only one operating point. And as the correlation between current, torque, voltage and speed is nonlinear, especially when you are coming into the field weakening range here, it's very important that you have the information at hand sometimes before you start building your machine. So the tool also allows for picking certain operating points, for example, back here, 350 Newton meter at 5,000 RPM, and checking or giving an output what current in ID and IQ, for the guys which know the control of permanent magnet machines a bit closer, and the voltage you need there. So you can check on safety levels, you can check on control level if this is still reachable. For example, if you want to use a different inverter than the one we can supply with the motors. So it's a tool we give to our technical sales team, internal of HYDAC, to be able to answer a lot of questions you might have before you actually buy a specific motor. Something as of the nonlinearity cannot be deduced just from a data sheet you might find online. Now, Fabian basically already told you which motor is right, but I still want to dig a bit deeper into the reason why the choice he made is the right one with his team. He started with the 260W 2020, which we see here down. So this is a motor which is actually 200 millimeter in active length and has a nominal current of roughly 200 amps. The fact is that we can therefore use a kind of small inverter, one of the smallest one we have in this power range. But as we see at 2,800 RPM, actually that works. But in the higher speed range, we drop below the torque range of the combustion engine. So in case if this area here is just an overload operation and the application actually doesn't require it, we could use the 2020 motor at 700 volt and actually operate it with this combustion engine and therefore benefit from a smaller inverter. And then if you look at the torque, the other solution he chose is the 2014 P here. This is a performance motor we have. It's a differentiation of the 2014, which has a little lower performance. So we have internal changes in the motor which allow us to exploit the volume of this motor in a better way. We see that we get actually with reducing the number of turns from 20 to 14, what I explained you earlier in theory, that the nominal point drops to a higher level at the cost of increasing the current to roughly 300 amps in that torque range, and therefore we need a bigger inverter here. So it's something we can apply to, but the motor doesn't change, the size doesn't change. Outside you don't even see a difference, but inside we have a different turning number and therefore higher current, and therefore can reach this operating range. Something which could be then the case is that you might want to go at a lower voltage, or that the application, a customer requires this set to be installed in a vehicle with 350 volts only, so half the nominal voltage. And the problem would be that with these motors, you wouldn't be able to reach that operating points again, while the torque is actually sufficient. And then we need to go even further down in number of turns. So I actually added here the 2010 motor at a nominal voltage of 350 volts. So from 2020 I halved the number of turns, and therefore at the 350 volts, half the voltage, we get a very similar operating curve here. So we could go even down to a 20007, but I didn't have sufficient measurement data available for this motor, so I prefer to stick to this one here for the webinar today. And we can actually, with the variability we have, with the same volume, same inverter, because this inverter is actually able to also supply the higher current in a different version we are selling, the performance at half the voltage. So without changing your mechanical interface, without changing the combustion engine, you would be able, within the range of motors we can offer, to supply actually that power both at 350 volts and 700 volts to your customers. So this is, we believe, a very big advantage of this modular approach without having to change the design of the machine on a mechanical point of view. Ending with this, we would like to go to the next study. It's a hydraulic case, and we would like to start with the technical side on the hydraulic side. That's not our expertise. We got explained a lot from this from our partner HYDAC, so that together we can actually offer here very interesting solutions. And we will quickly start with the hydraulic part, but then we'll actually go into the details of the electric motor requirements from this side.
Thanks. All right. Yeah, now focusing on the hydraulics part. So hydraulics required a mobile machinery for different kind of work functions, lifting, bucket, steering, as also some of the side functions. Even particularly we have applications where hydraulics is then used for traction too, but in this case we're looking mainly, so specifically on work functions. So here we see one of our hydraulic pumps within our portfolio. PPU 100, and so obviously you see we're not the largest pump experts, hydraulic pump experts, but we finally we analyze what is required to operate such kind of pump, and there we have a good engineering transfer then to the requirement story. So looking at this specific exemplary case, so you see right now we're changing the battery voltage. This is for a good reason, because we don't want to show you samples. Today we want to show you very special samples where it might make a difference, change for different kind of motor variations and variants. And today with this one, it's a good showcase too. So effectively, battery voltage level 400 volt, coolant inlet temperature 60 degrees for water-cooled motor. Pump specification, in this case, 250 bar is the maximum pressure which is required, and then we have a reliable flow rate requirements of 10 to 45 liter per minute nominal. And you see the characteristics here. So effectively, first of all, looking here on the flow rate. So flow rate 10 liter and going up to roughly 45 liters per minute, and then the pressure 250 bar. And this allows us also then to finally concretize obviously the need for the power consumption or the energy feeding by the electric motor to the hydraulic pump. So transferring, let me say, the hydraulic requirements from the pump to the motor effectively means that right now we're talking about nominal power range from 5 to 23 kilowatt and a nominal speed range from 600 to 2500 RPM in the end. One of the major benefits which we see before we deep dive a little bit more on the next slide is that with the electric motor in combination with the hydraulic pump, you have significantly higher possibility to react to different kind of duty cycles inside of the machine for the hydraulics, and this also allows in the end that you can increase efficiency, because you can adjust the flow rate, you can adjust the pressure much more flexible than you could do it in the past with a combination, for example, with diesel engines. So the electric motor allows you much more flexibility on the complete operations cycle. And this is also what we show then here in this pump characteristics analysis. So effectively, we selected based on the information we had before that 205W motor 08052 is the ideal choice to be operated at 400 volts. So we see here right now the plot characteristics. there it is. So we see on the blue line, we see then the nominal torque and the peak torque, which is maybe not that, not the, let me say, the best numbers compared to what we have seen before. So we're more looking at the moment on the power classes. So 5 kilowatt, as mentioned, for the operations point 1, and then here at this point 23 kilowatt for operations point 2. And between this, we're moving then on the continuous level of this motor. And with regards to the speed allowance of this hydraulic pumps, we can even go up to flow rate then to 3,400 RPM. So we have higher capability of this motor inside of this complete pump characteristics. And this is what we see here on the middle part. So effectively, the green area is describing the continuous power range, and the red area is also describing the peak power range. The continuous power range means effectively that with the electric motor in combination with this hydraulic pump, we can drive from a lowest pressure, from highest flow rates up to 60 liters per minute, down to roughly 55 liters per minute maximum, and this to pressures up to 250 bars. So dependent on what you are doing currently with the machine, and even considering that hydraulics functions goes on standby, you can then reduce finally the flow rate, you can even reduce the pressure, and by this have significant efficiency gains on the machines. And on the other side, with the electric motor, is also allowing you for a shorter period to finally go for higher requirements. So over exceeding then pressure, going up to absolute limit maximum then for this pump for 300 bar, and also allowing then for increasing the flow rate for a short period of time, for example, to 60 liters per minute, which may be sufficient for some specific requirements like short time lifting of a bucket or whatsoever. Yeah. This is one example for a swivel motor in this range, and Bernhard will show then on the next slides how the separation of the variation of the motor can also help for alternative applications.
Yeah, so we're just looking at the basic choice of the motor for the application, which Fabian explained. So we came to the conclusion that the 205W0852, it's the motor which Fabian was talking about, at 400 volt matches that performance very well. So not to confuse you too much, I'm sticking to the torque curve, even if we're speaking about power here. So you don't need to rethink what's actually happening if you now change voltage or number of turns. And but what we see here is the continuous torque curve of that motor with an inverter. The current is roughly about 90 amperes, so the inverter here would be absolutely sufficient. What could be an application case, and we actually had that in the past, and we still have it current with customers now discussing, is that the solution you build up, you want to sell to a end customer which actually doesn't have 400 volt but 800 volts. And so what we would expect, what happens, is that the continuous torque range with some AC loss effect is actually just doubled to the nominal speed of now 8,000 RPM rather than 4,000 RPM. So this is the expectation, and therefore same current, same motor, same inverter, you can just supply that to a different customer. Unfortunately, what happens is that at a very large voltage steps, certain AC losses, which are nonlinear, depending on the voltage to induction ratio of the motor, are kicking in. So if we just slightly increase the voltage as shown in the curve here by some percentage, we do have a slight decrease of the S1 torque in the base speed range, and we have the expected increase of the nominal point in the speed above the nominal speed. So this is what we expect. But when we go to a larger step from 400 to 800 volt, what can happen is the different parts due to these AC losses of the motor are the thermal limiting factors. And in this specific motor here, we are actually getting the S1, so continuous non-stop power you can run with that motor, with all the parts of the motor in thermal limitation in this dashed black line. So actually, instead of just increasing the power range to 8,000 RPM and keeping a constant torque, from starting about 2,000 RPM, we see an additional limitation of the motor performance due to other parts limiting the thermal behavior, which need to be protected. What you see also, what I show in this slide, is that the S2 30-minute power is less affected. So some parts are heating up in the motor much slower than the limiting. The limiting factor is actually heating up much slower than some other parts, for example, the windings in this case. And therefore, if we only operate the motor for 30 minutes at that power, we're getting a much higher torque. So here we see that more expected behavior, that actually the torque goes down slightly because of the increased voltage, and then the nominal point actually goes to a higher level. So with that motor at 800 volt S2 30 minutes, we're still getting in the range of 75 to 80 Newton meter. So the application might be still possible, which we had before, which was 85 Newton meter continuous, while as S1 continuous power, that is not possible. So you would say, okay, that's an issue. So I cannot really profit from a modular motor approach. But actually what you can do then, or what we can do for you, is that we actually increase the number of turns to roughly the double, because the voltage doubled. It's not exact, and it's not exactly double the voltage because measurements of that motor were available at a different voltage level. But we see here the curve of our 08095 motor at 700 volts in violet. And then we are actually back at the performance curve of the 0852 at 400 volts. So with a reduced nominal current of roughly 50 amps, then we are able to get again to the same continuous S1, so non-stop operating curve than before. And all this within, again, the same operating range. So the fact is that there is some nonlinear loss effects in the machine, which lead to the fact that with increasing the voltage too strongly, we might get ending up with a lower performance than expecting at lower speed and also at high speeds because of these limiting factors in the machine. It's very important to know which parts are limiting and also at what voltages this is important. And something else which can happen in variability is that actually you realize that the power you were designing the machine for at the end is not sufficient, and how we can help there with a modular factor motor approach is shown on this slide. So let's assume during prototype testing of the machine, it's realized that the flow rate is not enough, which was expected. So you would want to increase the pump displacement to get a higher flow rate at a constant speed and therefore more hydraulic power. But that leads to the fact that you need more torque at the motor shaft, which we can solve with an increased length. And you see this here at this point for a motor length of 80 millimeters and 120 millimeters at a constant number of turns. We actually go up in the operating range of torque, and we can then increase the flow rate of the pump and be able to supply this higher power with the same interface, with the same inverter at same current, but at a higher torque level. What you also see here is that the motor length has also a nonlinear effect on the torque increase, because AC losses again are kicking in. So in this mid-range here, before field weakening starts, actually the torque increases higher with the higher length than at lower speed, because the inductance is actually helping us. So the motor length increases the inductance, reduces the AC losses, and therefore we have a higher increase of torque here in this mid-range.
Before we move to this slide, I just want to add some to one item in the end. So specifically looking at this scenario with different voltage levels. So obviously it's something where you may start on operating on 400 volt, and then you decide, okay, we want to increase the voltage level. The important thing is also here, so we're changing the winding configuration, but the complete dimensions of the motor keep the same. Yeah. So effectively, we have the possibility to keep the packaging completely equivalent. Also with comparison, what Bernhard then mentioned, the other slide for the mechanical interface, complete equivalent interface, equivalent dimensions, also on different voltage levels. And this is also what helps then for your application, so that effectively, at least the packaging part is not challenging for the final application anymore. Moving ahead, not back, but ahead to the next slides. So looking at the traction part, as mentioned, we have prepared two scenarios. One scenario is a direct drive traction system. Second one is a traction system with transmission support. And we're starting first of all with a direct traction drive system. In this case, we investigated heavy-duty machinery, which is typically operated in mining grounds. So we have high traction forces because we have a heavy machine, we have high loading effort, loading forces, which need to be considered. So we did some analysis on this one. And finally, so we see three different specific set points for this application. Obviously, there are many more, but let me say for this kind of case study, this is what helps for a more comprehensive understanding. And then we see the maximum traction force. This is the behavior for high gradability at low speeds and a full load application scenario. Then we see the continuous traction force also at a full load scenario, but at a higher speed and at a lower gradability. And we also see then for the maximum vehicle speed another set point. So the peak set point is something which not just need to be provided for some seconds, for example, to drive over stones or some other barriers which are on the road. Then we have a second one where we see then the continuous traction force, so the typical duty cycle which this machine is operating with regards to the traction system. And last but not least, even so this machine shall operate at a quite high speed. So looking here at 20.5 kph and still having high traction forces applying. How do we solve that? In this case, it's something interesting because we see that two different motors fits these requirements, but there are some major differences. So we have the 370W series. So this is the low speed, high torque motor, which we just introduced. And this at the same length, so 290 millimeters active stator length, and then in different winding configurations. So 12P, so winding turn number 12, and then as a performance version, versus 16. And this combined with one of the most powerful mobile inverters you can find on the market. You see here in the lines, so the dotted lines is the peak, obviously. So the yellow line is then for the 16 winding configuration. The blue line is for the 12 winding configuration. And the same also for the continuous aspect. So all in all, looking at the maximum traction force, so this finally fitting in both motor characteristics. Also for the nominal set points. Yeah? So for the continuous traction force versus the maximum vehicle speed, this also fits in both scenarios. The difference is, looking at the next slide, that finally with the different kind of winding configurations, you have now the possibility to improve even the vehicle functions. So you have the possibility to say, okay, I want to have higher gradability on the vehicle, so 14.3% is not sufficient. I want to go, for example, to 70% or even more. So then the 16 winding configuration would allow you to get to the set point, what you see here. At the same time, you then going for the finally leading to the reduction of the available nominal speed range. So effectively, so this is restricting you to 20.5 kph. Or you're finally deciding, okay, my machine needs to move faster, but then the gradability is not in the major target. So effectively, we could then, with the same motor, with the same reduction ratios over differential, we could then finally achieve that the vehicle is speeding up, going to a faster maximum speed level, but then the gradability of the vehicle is more limited. So it's kind of trade-off finally what is associated with this kind of machine. But having different motor variants possible, we even have the possibility to get more out of your machine. So finally, the requirements in this case were coming from the customer, And with the solution we're offering, they are offering even more added value because we're giving more capability in one direction. So more gradability or more vehicle speed as reference.
Yes, and to point this out a little bit more clear is we see here again the measurement results from our test bench on that drive, and what I added here is also the efficiency curves of the motors. Something which is very interesting to see here is that actually in the low speed range the efficiency is very similar, and here again the higher torque, the continuous torque this motor, the 16 winding is offering, is due to different thermal behavior in the machine and therefore a lower limiting factor at that lower speeds. So you can achieve below 500 RPM, nearly 2000 Newton meter continuous, and the higher torque here, 3800 nearly at the lower speeds. But what's also interesting to see is that at higher speeds the efficiency drops. This is very drastic here because at 3500 RPM actually the continuous power due to the losses of that motor is nearly zero, and then the only thing you do is actually supplying losses to the machine, so your efficiency drops drastically. I compared this also at the peak curve. We're having a difference of roughly 2% due to the higher current needed in the field weakening range. So you can still drive here and your machine efficiency won't be actually 55% there. It's just that at nominal operation S1, if everything's heated up and you still want to drive here, you basically don't get any power out of the machine anymore and you just push losses in. So this is an additional effect with the winding numbers. We can play with the efficiency of the system. And so depending where on your operating range you are and what your needs are from your application, we can tweak that and optimize that for a later application. So we might start with a motor available, with a motor which is the parameterization set is there, it's ideally in stock, so you can quickly start with your prototype, do the testing, and if the volumes go up, we still have possibilities in the modular manufacturing approach to optimize your design. And that was one of the idea of doing today in this webinar, to show how you can even profit from this modular approach in terms of machine efficiency, and not just that we sell a lot of motors, have a lot of variety, which at the end is still difficult to manufacture, and you don't actually profit from it at all. So Fabian already mentioned it. Besides just looking at the direct drive with just a differential and no gearbox, we want to show you a second solution, how you can actually approach the attraction drive, and how we also can, again, with our modular design and with the variety of motors we have, offer you solutions there. So the requirements here are very similar, but a little bit lower. This is a real case story from a customer some time ago, which we discussed with them with different solution possibilities. You're seeing here, again, a high traction force at low speeds for transporting, for example, something in a truck or a wheel loader. To have a continuous traction force at a medium speed with a loaded vehicle, and then a quite low traction force at a high speed, which is, for example, an empty transfer travel with your vehicle from point A to B, but it's not loaded. What's interesting here, we do have two solutions which can handle that applications. One would be the same motor which we were discussing before for the generator, the 260W 2020, with a 200 millimeter active length and an inverter with roughly 200 amps. So you see here, this motor is able to provide both the continuous torque at low speed, at high speed, and the overload. But you also see that it's basically 50% over-designed, because we still need to be able to reach that torque here at the high speed. So by having the advantage of not needing a gearbox, we buy the disadvantage of oversizing the motor, making it bigger, and so that you can achieve actually both applications. And this is mainly difficult in mobile machinery, because the load, the torque at low speed for transporting, for working, for doing something actually is much higher than, for example, an electric vehicle, where this requirements are also differentiate far away from each other, with high speed and high torque at low speed, but not that extreme. So what we discussed in case of this customer to see how we could get down the costs in the system was what would be if we would add a gearbox. And what we could show is that actually with a 2-speed gearbox, we can actually, with a much smaller motor, so we're speaking here also on an active length of 200 millimeter, but from the 205W series, so much thinner, smaller diameter of the motor and lighter, with 2 gears, instead of actually having a total ratio of 21, we have one gear ratio of 60 and the other one of just 20. So for the low speed operation with high torque, we're having a first gear set covering these two applications, and then for the high speed driving, we have a second set of gears which is able to provide that speed. And what you see here again, we can even drive faster with that vehicle because we don't need to go so deep in field weakening. And if you remembered from the slides before, that I said that in deep field weakening also efficiency goes down. There's also an efficiency advantage in that machine doing that with a gearbox. But of course you have a mechanical part which you need to add, but you can downsize the electric components, speaking here of an inverter of only 90 amps rather than 200 amps and a smaller motor. Summarizing this up, there is both possibilities. So depending on the focus you have with your machine, do you want a gearbox? Is a gearbox available? How fast do you need to start? How is your volume, your envelope of the machine? What's the weight constraints? We can go all for a direct drive without a gearbox with a bigger electric component, so good for us because we sell more. But we can also go for a smaller motor with a smaller inverter and then a gearbox to actually downsize the electric components. So the overall weight of the machine of the drivetrain can stay the same, can get smaller, but packaging sometimes gets easier and cost on the electric side can be reduced. We can do that up to an extreme that we go down to 48 volts, but we just introduced that motor not long ago on our internet site where we go to 40 kilowatts, I think, for 48 volts. But as this takes some time to explain, we want to skip that. But if you're interested in knowing more about the possibilities we can do there, even with lower voltage, 48 volt and maximum power with up to 1000 amps on the machine, just let us know and get in touch with us later. Something which is also important, and I want to quickly point out because we speak a lot, and I'm an electric engineer, so that's my passion about the electric performance and how we design the performance charts of the motor. We also should not forget the mechanical part of the machines. So combining our motors with gearboxes, we need to look at the possibility of actually getting damages in the mechanical parts. And something which is very important to know is that in an electric motor, you saw that in all the performance parts earlier, the peak torque is much higher than the continuous torque, something which differs from a combustion engine. And if we are driving a machine with this kind of V cycles where we have very high loads for short time, but the average torque is actually very low. So here we are roughly speaking about maybe 50 Newton meter average, but 380 Newton meter peak. This might strongly affect your lifetime depending on the safety goals you're actually focusing. So here, this is an application in which we were doing this for a customer which wanted to combine our motor with a gearbox. So the motor has an external spline on the shaft, the gearbox had an internal spline, and the discussion was, is that spline big enough to actually withhold that load? And what we can say, yes, it is. Unfortunately, it will break down after 4 hours. So I don't know if this is what you're actually looking for, or if we should not look actually for a different bend shaft. And we were actually working out a solution which could work out here, but it just shows, yes, if you reduce the torque to 320 Newton meters, you already get 200 hours. And if you see here, if we are reducing the safety factor, we get even 10,000 hours at that time. So both safety factor and the maximum torque you are applying to that device is very important. And the drive cycle and the peak loads have to be considered to be sure that we are not designing something which will break down too early. So this is something we can do as well. That's more the mechanical part of our job and what we are considering typically as soon as we are looking into deeper details. But again, as we mentioned earlier, if that machine with that shaft is available, you could start with the prototype testing, integration, do first runs, and you might not have an issue with that possibility of early breakdown. In the meanwhile, we can actually use the time to design the machine for the final application. Finishing with this, I want to go, and it's another passion topic for me, the influence of the inverter control on the machine performance. And one thing you might have noticed that newer data sets, data sheets you find on our internet site are most of the time or always now combined with a typical inverter, because we do the testing and the parameterization on our test benches and we create the performance plots together with an inverter. And why are we doing this? Because the inverter has a very strong effect on the performance of the machine. If we are looking at that slide, and I'm not going into detail, but trying to just give you the feeling about that, we introduce in our tool, in the MCA, our technical sales teams is using a modulation factor. And this modulation factor accounts for the fact that the inverter is not able to fully utilize the DC link voltage applied to the machine. This might be due to internal control specifications, so the controller were written in a way that they can't use it fully, to too long AC cables or some other issues. But what it effectively leads to is a lower continuous and peak torque of your machine. The effect is stronger in the peak torque range, but because here that points between peak and continuous torque you still reach. Once you're reaching the peak torque curve, there's nothing more you can get out. So actually, you will feel more that effect at the peak torque curve than a continuous torque, because continuous operation you will only see at the end when the machine is fully hot, but the S1 power will be lower, can be lower, or is strongly affected by the control. There's other factors than this modulation factor is the modulation strategy. So typically we are operating with variable frequency drives today, which have a PWM generation internally. And depending on how that is done, you can shift losses from the inverter to the machine and back. We do have simulation models where we can show what happens if you, for example, change the frequency of the switching or this modulation strategy. And this also leads to the fact that you might, with a different inverter and a different setup, actually get a different continuous and peak torque curve compared to what you will find in a data sheet. So it's always a question also with what kind of type of machine this kind of performance plot was generated, with kind of if it's test bench results, if it's simulation results, and if it's with an actual inverter. And so what we are doing at NGiro is that we are setting up our motors together with our series inverters. Typically, we are getting parameters from simulation models to actually speed up that testing process. And then we go at our test bench to verify if we combine an inverter the first time with a motor in our test bench to see what happens. And in the worst case, if something goes wrong, if, for example, time constants of different controllers in the inverter don't match the motor, even if we verified that in the simulation model before, this can happen due to discretization. You might end up with a performance plot looking like this, where you have a drop or a dip of torque and power in the medium speed range. And after optimizing the parameters, we could actually reach a much higher torque and field weakening. So here we're speaking about in the 10th of kilowatts, we could get more out of this motor, and we didn't have this drop anymore. And that's quite simple to find on the test bench because you have a measurement device. If you're searching something like this in a vehicle, that gets really hard. And yes, Fabian?
I have one question, Bernhard. So some of the inverter manufacturers are also offering auto-tune functions. Can you explain more in detail the differences between a fully validated setup of inverter motor versus an auto-tuned selection?
It's a very good question because this is the second example on this slide. Yes, there is this kind of auto-tuning, and up to the nominal speed, typically this works very well because this is actually having an internal model in the machines. It runs at no load some tests on the machine. So the inverter applies some currents to the electric machine, and with the voltage response of the machine, it's estimating the electric parameters of that machine. Every inverter supplier does this a little bit different. And what we see here in the plot down is that actually in the no loads, in the speed below the field weakening range, so the nominal speed, that fits very well. So this is actually on the left a setup on our test bench where we just did the auto-tuning, ran the motor, and well, if you do a MTPA, so maximum torque per ampere validation at low speed, everything looks good. But once you start getting in field weakening, we had a major drop in the performance, and here we are basically speaking nearly about 100% drop of performance. And what was this due to? This is actually because in field weakening, as the angle of the current changes in the machine, different inductances and saturation parameters kick in. And this leads to the fact that it's very difficult to estimate this in no-load operation. So here with tuning some tables and with tuning some controllers in the machine, we were able to increase actually the performance of that motor and inverter set strongly. So yes, auto-tuning helps. If you want to set up a prototype very quickly, get up something spinning on the test bench or on the table or in the machine and runs. But if you really want to get the maximum performance out of your vehicle, you need to go to the test bench, in my opinion. Okay. And on the next slide, I want to show you, or we will show you a short video of what we are doing. We heavily invested together with our partner HYDAC on the in our test benches. So you see a short video of this activities there. We built 4 new test bench chambers where we can run from 48 to 800 volts. We have 2 power supplies with up to 140 kilowatt per power supply, so we can run in parallel. You see here our headquarter with our R&D and assembly, but you will see this later on again if we will look at the production. These here are our test bench chambers. And they are equipped with handling devices so that we can quickly set up different motors, because sometimes we are changing them 2-3 times a week depending on what a customer requires. We do additional customer-specific measurements, but we have also a 3 to 4 day measurement program we do on a motor when we characterize it the first time, to actually do a peak torque test, as you see here, or do a nominal operation tests with different voltages, different cooling requirements, different speeds, different flow rates if it's an air-cooled motor, to actually somehow compile a measurement report, which we then can supply to our customers, so that even not having tested everything, but because this is impossible, every operating range at the test bench, we are able to estimate the performance to be expected in the machine as good as possible with the lowest effort as possible, so that we can effectively go further. What we also do at these test benches is validation tests, for example, homologation tests for ECE R85 for street vehicles, but also other validation tests if required. So if you want to wrap it up, what we do for our customers.
Yeah, thanks, Bernhard. Yeah, so finally we have shown several case studies, and by this I think we hope we make clear that first of all, inside of Engiro and HYDAC, we have a lot of knowledge with regards to electrical motors. So we do all the motor design in-house. We have a long experience in this approach. We have specifically focused on the modular motor design, which allows to help in a lot of different application scenarios inside of off-highway mobile machinery equipment. We combine our knowledge with experience. On the one side, we are collaborating a lot with our local universities. In Aachen, we have engineers who have studied there with very good reputation. On the other side, we doing this for a while already. We have supplied more than 7,000 motors in field operations. And by this, we have gained a lot of experience with regards to not just the motor, but also for the inverter. And inverter is, as Bernhard just have shown, is a key part for us. So we are typically trying to give you a setup which is fully validated, because then we also feel comfortable that the performance can be achieved, which we also give with the performance plus we provide. And thereby we're helping also with other inverter selections if our in-house inverters may not be the ideal solution, which is not that often the case, but nonetheless there are some application cases. So in such kind of cases, please feel free to contact us too. And besides that, also the in-house knowledge level of inverter side within HYDAC is increasing more and more. So effectively, we see us as a system supplier, as a drive set supplier for electric drive set solutions. The other aspect is, so we are not just talking about fictions. We are talking about motors which have been developed, which have been validated, which are produced, and which are also partially on stock. Not everything is on stock, because with more than 100 variants, this would be a nightmare. But nonetheless, we are typically also in a situation to deliver, especially for quicker setups, so first prototype mockups and something like that, also faster options out of stock. And obviously, documentation is also part of key. So we have gained a lot of knowledge on our test benches, we also implement that in other items like measurement reports and simulation tools. So we push our knowledge through our HYDAC colleagues globally, so that doesn't matter with which kind of sales colleague you talk from our global sales team. Finally, we just expanding our experience level to our complete sales network worldwide. Okay. And Bernhard, then it's a lot of interesting aspects with regards to the products. It sounds really sometimes crazy about modularity. So I think there are some members in this board which says, okay, modularity and flexibility sounds super exciting and super interesting, and it sounds super expensive. So how do we solve that topic, especially for the manufacturing part?
Well, thank you for that question. But I mean, if we wouldn't have made those slides together, I wouldn't know that the question will come. So yes, how do we actually manufacture that flexibility? I mean, the point is we partnered with HYDAC, or HYDAC acquired Engiro and majority shareholder 3 years ago, because they are active in that market already and have manufacturing experts which can help you there. But the idea is, of course, you need to also design the product for the fact that this is actually working. So what we are currently doing in the situation now is that we have our R&D in Aachen, where we do have the assembly of the 370W motor. We have our design team sitting there doing the motor design, the testing. You just saw the test benches, and also we do make validations here, end of line testing of the motors. In addition, currently our motors, all green motors, which are not the 370W, are produced to a subcontractor in China, which build up a strongly variable production line, mainly manual for us, with which we handle the current production volumes, roughly around 4,000 to 5,000 motors a year, and we can still expand that up to 10,000 motors. So this is for the 159, 205, and 260s. But of course, most of our customers have very demanding roadmaps for electrification in their program, and we want to participate in that market. And therefore, we're expecting growth. At the moment, it doesn't look that good on the short term, but in the long term, we're speaking with a lot of customers with bigger growth. And therefore, the question was, how do we expand that? Both in terms of the local for local strategy, HYDAC is already driving in the other components they are building, but also in terms of resilience of supply chain and higher automation level, and for certain applications also higher quality level. And for that, we started in plans to extend our Aachen plant with a second building to be able at the end to produce there, depending on the shifts and the final machines installed, between 15, 32, I think the maximum number is roughly 90,000 motors if we really go to the full extent of what can be in terms of building and machines installed there. And well, you might see a nice vision, and on the slide before you just saw a CAD model of the building, but actually it goes really fast now because building already started. This is a picture from 2 weeks ago, which is already not correct anymore, because at the moment the factory plant is closed. So until the end of the year, we believe that it will be a finished building for the production side, and we can start inside building, and we will build up the whole machines and start producing there at the beginning of next year. And what is really important here is that, as I said earlier, you need to design the machines which you put in that factory, plus the motors, in a way that you can actually do that, scaling up instead of just increasing cost and keeping with very manual labor. So the main factors here is, or the main parts in the production are these 4 parts I stated here on the left. We start with a stator assembly, where we actually start with single sheets. And with the single sheets, we can then get different lengths of stators. And we are working with a winding process, which is independent from the length of the machine. So it's a process which is also used in automotive industry. For example, BMW used a similar process for the i3 production with several 10,000s of motors a year, but the same type. And we adapt that, together with the supplier, that process in a way that we can actually build different machines without having to change tooling all the time. The same thing accounts for the impregnation. So we're using here also an automotive process, with some difference in material because we are using higher powered material in some parts. But the difference here with an automotive line would be that we don't need any tooling, and we can produce all 4 motor lines we have, all 4 motor sizes we have, no matter if it's 159 WH or 370 without any change in the machine. They can even be produced at the same time in that line. So this is an optimization which we did here, and a focus we did in the production line. Same accounts for the rotor assembly, where we also took care of the automation level to make sense in terms of investment, but also in terms of how we can handle the different shaft types, because we saw we have spline shafts, we have flat shafts, we have different lengths and different magnetization tools for the magnets, so that handling is good, that the balancing, for example, works partially automatic, so you don't have too much work labor here. And the same for the assembly line at the end. This is something we did use from the 370 assembly line we have now. So it's already in production at the moment, in testing, if the processes work. And we'll see this shortly on the next slide, that we already do get experience now how it works. We can tweak that, and we can actually change that on the higher numbers on the next slide, in the next year, sorry, not slide. And so that you get a feeling of what we are currently already doing in Aachen, we compiled a video of our current production of the 370 in Germany, and I would like to show you this now for the next minutes. So again, we will you see our current building at the beginning. Shortly after, you see this motor. And in the back, you can also see the building site of a factory. And as I said earlier, some of the production parts, for example, impregnation or winding insertion, at the moment we're still doing with external partners because we don't have the capacity to do this on ourselves. But then the testing of the parts, again, the design specification and the assembly actually happens in our motor. And we just got a question about this, which is from the audience. The current capability of production is 8 370 Ws per day. So we can already produce a significant number of motors per year. And you see here the heating up of not the stator. So this is the stator. The housing is heated up to actually put over the stator. Then the cables are connected. The connection board is added. We have tooling devices or handling devices so that the motor, with its weight in total at the end of 300 kilogram, can be easily handled in production. We apply the side parts, and this kind of processes will be similar in the final production line for the other motors as well. And so that the processes are similar for all the motors, so that tooling can be the same. Of course, handling is different if we speak about a up to 600 kilowatt nearly. I think 580 is the maximum we measured on the test bench beast of this motor compared to a small 10 kilowatt motor, but the processes, the ways of doing it, and the testing of the processes, which were developed strongly together with experts from HYDAC, we are already doing at the moment. So reduce risk while we are actually setting up that factory later on. So I think what's important here is that when you do something like this, you need a certain competence, both from the production sites which we are getting with our partners from HYDAC, with the production experience we already have with our partner in China at the moment, and with the machine suppliers we vetted and we chose for the different the production machines in the factory. It's also a dedication. I mean, it's a huge investment, a new factory like that in Europe. And at the same time, we also want to continue work with our existing partners because we also have to demand to supply directly for local production. As I said earlier, HYDAC is already running a local strategy and other components. And the long-term strategy is to be also able to do that on the motor side. It also helps with resilience. If something happens, we had that in the pandemic 2019, where you weren't sure if you could get anything out of China anymore, or Suez Canal being blocked, or energy crises. This is things where being available in different markets in the world, getting a redundancy in your supply chain is very important. What is important too is the scalability, but this you cannot only think from the production side. It needs to be thought from the machine concept, the way the machine is designed. And also in terms of extension. So the building here is similar than with the building our current headquarters from Ingero, in a way that we can extend production capability, but also office space. So in terms that in the long term, if the market is going up, we still have the capability to react to what the customer would require. And at the end, it's flexibility which is required in the market. We think this is key because otherwise, as we saw in the first part and the second part of this webinar, for the market we are addressing, it will be very hard to compete. If you're just able to produce one motor without change 250,000 times a year or even more, that will be difficult to put that on exactly the right application in the mobile machinery and say, okay, you can't change anything there. That's not what we do. That's not what we did in the past, and that's what we want to keep on going for the next years.
So long story short, we're building one of the most modern motor manufacturing lines for the off-highway industry currently in Germany. So it's a large commitment, and contributing to the future success for mobile machinery applications in the market, and keeping by that also the high flexibility on different machines. Okay, so we see here some questions. So one question has been already been replied by Bernhard. So production capacity of the 370W at the moment 8 motors per day.
Yes.
Yeah, so 8 per day. And then calculating by the days, that's something you can do on your own in the end. So for next year, we are planning also to get at a very similar production level for 370W series, and then with the new manufacturing plant, we will have the possibility to increase the production capacity of the 370W. So looking at a production capacity for 2,500–3,000 motors a year, just from the largest motor in our product portfolio range. I hope this is answering the question properly. And do you have further questions? So there's still some time left. So we have right now 4:36. It's 50 minutes faster than we have been expecting.
It's always we're speaking faster than we should.
Exactly. So please feel free to have some questions. And then we check what's coming in right now. Lead time is one question. So with the lead time of the green motors, they are 26 weeks for a long time. At the moment, this is the lead time for the production in China. This is true. We are not happy with that too. So we want to reduce it as fast as possible, but we obviously also restricted a little bit by logistics. No, it's not our target to keep that. So we were also looking at reducing this lead time. And then with the new manufacturing plant in Germany, we also have the possibility to react more flexible, more faster on different kind of motor versions if there's the need to speed up deliveries too. So this helps us also for getting faster to the market.
And something we see, going back on the lead time question, is that the demand is also to get delivered directly from our Chinese factory. And the point is that this is something which is thinkable of, depending on the market you're in, if this makes sense. But also a question which is depending on the volume we're having. Because currently on the motors we have, we are building, we also collecting sample data, which is required for being able to assess the quality and the stability of the production process. As certain parts, we only do assembly at the moment in Aachen. So this is also in terms of preparation of our factory in Germany, an important part of running our motors through our German end of line, which of course, depending on where on the world you are based and the application is, and it is adding some time on the lead time. But in terms of volume, as long if the volume is big enough, if the motor is defined, if we are through prototype state, that's something to be discussed, of course, to also be possible to reduce that lead time.
And the next question is more technical. Have you got any product about hub electric motor you want to answer? I see already. So please go.
So I suppose you're speaking about a motor directly being able to attach to a wheel. Yes, we do have applications where you have an interface on our motor with where a gearbox, a planetary gearbox, can be added, and therefore you can use that combination of motor plus gearbox as an hub motor. And for example, the new motor line which we introduced, or we showed that we will introduce during the next year, has a partially focus on this kind of applications with a short active length, a little bit larger diameter, and then in combination with a gearbox to be also usable as a hub motor. Yes, so there is currently the main applications on the 159 AH so the motor you see on that slide here on the left with that gearbox interface with a spline shaft and also possibly with a sealing on the shaft so that the gearbox can also be running in oil and be still closed on the shaft side.
Okay, then next question goes more deep dive right now in the inverter control items. So what is the gain of torque tuning about torque validation on the test bench on this in approximate percentage?
Well, this is a very tough question because it really depends on the reference you choose. And I always like to say as an engineer, choose the reference wisely. As bad as the reference is, then your gain is big. But more seriously speaking, with typical inverters in the market and not inverters which are bad inverters, just not matching of the controller software and our motors, we see possible increases in the field weakening area between 25 and 75%. The latter is really the extreme where actually you can't reach an operating point anymore with that reduced control quality because the voltage is depleted and you don't reach that anymore. You saw that in the 370W2916, that then at that point you basically just push losses in the machine and you can't actually get torque out of it anymore. But typically with voltage reserve and with optimizing control, it's roughly in the range of up to 25%.
Okay, so now more questions coming in.
Quickly, the first one question I saw about the sealed motor. Yes, we do have certain options which do have a shaft sealing. So on the shaft side, there can be added a dynamic sealing which is able to withstand oil or water. This is different because sometimes these sealings, if they are dynamically closed, they need to be lubricated. But if you have more questions about this, feel free to contact our sales team. They will answer and show you the options available.
100%, yeah. And then looking at another question, do you know? Do we will propose inverter with specific command, random MLI in the future in order to limit the THD? Do you understand that question?
I'm not sure if I understand. I can interpret and I say, currently the inverters we have, they have a specific control. And most of the inverters don't offer a differentiation in control method over the control interface. So it's a parameterisation a switch in modulation strategy to limiter harmonics. So this is, then I got it right, is currently in the most inverters not possible. We are internally working actively with different partners on a inverter strategy, and we also have our own product at hand. And of course, in this combination of the HYDAC internal own product plus our motors, we can optimize the control in the medium and long term to actually reduce the harmonics on the motor side. Because as you saw, and as it's also discussed in the automotive industry, by adapting the control, by adapting the circuit in the inverter, you can actually reduce the harmonics and therefore increase the output of the complete set. But this is only working if you combine both together. Typically at the moment with the low volume we have in the off-highway industry, Even in the and with the added costs of additional parts, this is not done on the hardware level, but on the software level, certain features are available, like optimizing of the switching frequency, optimizing the modulation strategy.
Okay. So looking at the time being, maybe if you want to take the chance maybe for one of the last questions. In the meantime, we're answering then the question about, do you also provide traction software alongside your drives inverters?
If you're speaking here about the system level, then yes, with our partner TT Control in Austria and also HYDAC software in Berlin, we are able to offer complete solutions for a whole vehicle. If this is what meant, so basically human machine interfaces with displays, taking in typical requests from a pedal or from a driving stick, and then transferring this via the communication channel to the traction drive. Otherwise, on the inverter level, there is different inverters in low voltage which offer the possibility to integrate that in the inverter. That's typically not what we are doing there. We're just offering the parameterization, and you can, if the inverter offers this, you can do this yourself. And the high voltage inverters we are having, they are at the basis traction inverters with a torque command and can be used in that way. So they're offering basic safety features such as active short circuit, over voltage protection, or a backup power supply, so that you can run that motors in field weakening at as a traction motor.